Hi everyone, welcome to Geometric Sequences. Now, if you took a look at the Michelson textbook, you've seen that we're not doing 1.1 and 1.2, and that's because that's a review from Math 10 where you did arithmetic sequences and series. You don't take a look at any sequences or series in grade 11, and then once again, sequences and series return back in Pre-Calc 12, this unit we're going to look at geometric sequences, geometric series, and then infinite geometric series. In Math 10, depending on who you had for a teacher, you may have learned a little bit about geometric sequences, and it's just another type of pattern that we're going to be able to explore, and there's a whole bunch of questions that we'll be able to look at a little bit more in depth now that we have a better understanding of how exponents work. So let's begin by taking a look at what makes a geometric sequence a geometric sequence. So here's an example. If we take a look right here, we have the pattern 1, 5, 25, 125, and the question would be saying, you might ask to say, well, what would be the next term, or how did you find out what the pattern is? And each time you go from one term to another, you'll notice that you're timesing it by 5. And that term there is called the common ratio. 5 would be our common ratio because every time you go from one term to the next, you're multiplying it by that exact same value. So I could ask you right now to list another example of something that could be considered a geometric sequence. So I'll do one right here. What if we had something like this? 2, 6, 18, blank. Okay. So if you take a look at the first term, we have a 2. To go from 2 to our next term, we're multiplying it by 3, and then we multiply this by 3. So then to find out what's going to go in our blank, we're going to multiply that by 3. And so 18 times 3 is going to give us 54. And that is what's a geometric sequence. So the constant called the common ratio, this value of 3 in this case, in 5 for the previous case, you use it and you denote it with an R for common ratio. And it can be found by dividing any term by the preceding term. So take a look at the patterns that we have right here. We have several geometric sequences, and they're saying find the common ratio. And so for probably most of them, you could just take a look at it and say, okay, well, times 4 times 4, oops. So my common ratio is going to equal 4. You could just take a look at it and you might be able to answer it right away. Right here, our common ratio is going to be 1/2. And if you said divided by 2, you're not wrong, but you want to say, what are you multiplying it by? And in this case, we're multiplying it by 1/2. If part C looks a little bit difficult and you're trying to figure out what your common ratio would be for that, what you could do is you could say, I'm going to find the common ratio of the numerator, and then I'm going to find the common ratio of the denominator. And -10 divided by 5 would give us -2. So our common ratio is going to be -2, and then 27 divided by 3 is 9. So our common ratio is going to be -2/9. And you can see it's going to oscillate between being a positive term to a negative term to a positive term, back to a negative term, and that's because we have a negative common ratio. Okay, so if we want to come up with a formula so that we could find out anything for a geometric sequence, let's take a look at the pattern 3, 6, 12, 24, and so on. And we can come up with something that we're going to call the general term. So I want to take a look at how you could break down each of these values here. So if our first term here is the number 3, and we're going to say our first term will be denoted by the letter A as we start to create this formula here. Then if we want to find the second term, we're going to multiply it by the common ratio exactly 1 time. And if we called the common ratio R, then we could find out the second term by taking our A value, our first term, and timesing it by the common ratio. So timesing it by R. So we'd have A times R. If we want to find the next term after that, our third term, we would have to times it by another common ratio. So you would start with the number 3, and then you would times it by r to get your second term, and then you would times it by another r to get your third term. And r times r would give us r squared, so you would have ar squared. And you could do that for the fourth term, and you would have ar cubed. And what you'll find is that your value of r, your exponent for r, is going to be raised to the power of 1 less than the term that you're trying to find. So for example, if you're trying to find the fourth term, it's going to be raised to the power of 3. And if you're going to try and find the third term, it's going to be raised to the power of 2. And if you're trying to find the second term, it's going to be raised to the power of 1. And if you're trying to find the first term, it's actually raised to the power of 0, if you wanted to say that. So if you're trying to find the nth term, it's going to be raised to the power of n subtract 1, where n is the term number that you're trying to find. So based off of this, we are 90% of the way to being able to create this formula for a geometric sequence. Our geometric sequence is going to look like this. It's going to be a, your first term, times by your common ratio raised to the power of n minus 1, and that's going to equal what we call t of n. And let's define what each of these parameters represent. So here's our geometric sequence formula, and you're going to be given this for all quizzes, tests, anything that you need it for. It's nothing that you have to have memorized. I'll start off by listing what A is. A is going to be our first term. N is going to be the number of terms. R is going to represent the common ratio. And T is going to represent, well, it's our answer, but I like to call it's our last term. It's what you're finding is the last term in the list of whatever they're asking for in it. Okay, now if you've looked ahead or you're starting to page through Michelson, you'll notice that he doesn't use some of the same parameters. Sometimes he's going to say, instead of saying t of n, he may use an L for the last term. And so if you see that, just know that they're equivalent to each other. And then sometimes for the first term, instead of using something where you would say A, he may call it A1, and then the term you're trying to find, he may call it A to the power of n. So it's something just a little bit different, but I think that you'll find universally that T of n equals AR to the n minus 1 is something that you're going to see a lot more often, and that's the way that we're going to refer to everything. Okay, so now that we have something like this, let's see if we can practice some questions from this. So here's a good example. Find the 8th term of the geometric sequence 3, 12, 48, 192. Now, if you're faced with a question like this on some sort of assessment, it'd probably be fastest manually just to have your calculator ready and say, okay, I'm just going to times this by 4, times this by 4, times this by 4, until you list your 8th term. So I think we need one more. 5th term, 6th term, 7th term, 8th term. Yeah, and you could probably find that out faster that way than any other way. Now, because we're practicing how to be able to understand and apply our formula, let's write this out, and you could say that we have, well, T of n equals AR to the n minus 1. And for the first time, let's actually write out what we have for our parameters here, just so we can make sure we can figure out what we want to be able to list. Our first term, A, is 3. Our common ratio is 4. And they want to know what the 8th term is. So we're going to say it's n is equal to 8, and we don't know what the answer to that is. So if we want to write this out properly, what you would say is this. Instead of saying T of n, you could actually write T and then a subscript 8. And that's saying we're trying to find out what the 8th term is. If you wrote T of n, that's totally fine as well, but it's the most proper to say something like T of 8 right there. And T of 8 is going to be equal to 3 times 4 to the power of 8 minus 1, or just to the power of 7. Okay, and so if you have something like that, then you can put that into your calculator, you can see what you get, and you should get something like 49,192. 152. And that's going to tell us that if I was to write out the terms with 3 being my first term, and I times it by a common ratio of 4, by the time I get to my 8th term over here, the value is going to be 49,152. So if you remember back to arithmetic sequences and series where you had something called a common difference and you would add common differences, when you're multiplying common ratios, your numbers can grow very, very quickly, and you'll see that the numbers get big very, very quickly, or in some cases very small very quickly. Okay, let's look at our next example. Okay, next example says the 4th term of a sequence, geometric sequence, is 125, and the 9th term is 125 over 32. Find the 13th term. Okay, so we have a couple ways that we'd be able to take a look at this. Just because we're getting used to this for the first time, I'm going to go a little bit slowly on something with this. So I'm going to say, here's 125, that's my 4th term. And then we're going to say, well, what would happen? Here's 5th term, 6th term, 7th term, 8th term, 8th term, 9th term. Okay, and if we wanted to go from 125 to 125 over 32, you may be able to see a pattern pretty quickly. If you're quick at being able to identify some patterns, you might be able to say, I think I might even know what the common ratio is just by being able to look at it from something like this. If you treated this where the 4th term, 125, you almost retreated this as your new A value. And you could say, well, here's my 2nd term, 3rd term, 4th term, 5th term, and this is right here my 6th term in this list of what we've mentioned, rewriting 125 as my 1st term. Then let's see what would happen using the formula. You could say something like, well, if T of n equals A times R to the n minus 1, and I want to find out the well, let's write out T of n, A, R, and n. And we have a bit of an issue here because we don't know what the common ratio is, but we know our 1st term is 125. We know the number of terms that we have is 6, but we know that our 1st term is our last term, is 125 over 32. We know the answer to T of n, but we need to solve for R. Okay, so if we have something like that, again, if you don't see the pattern right away, we could write out something like this. T of n is 125 over 32, which equals my 1st term, 125, times the common ratio we don't know, to the power of 6 minus 1, like that. And then they want us to be able to solve for R. Okay, so given something like this, what if we tried to get R on its own as best we can? So we could times both sides by 1 over 125. We could try and get this 125 onto the opposite side. And if we do something like that, so you times both sides by 1 over 125, then you're going to end up with something in which we could say 1 over 32 is equal to R to the power of 5. Now, from here, you want to be able to take your 5th root. If you need a refresher and you have your graphing calculator out in front of you, if you want to find your 5th root, you can press Math and then press the 5 button, and it should highlight something where you'd be able to get your 5th root. So press Math and then the 5th value down there, and that will give you the x root of something. So from here, if you have R to the 5 and you're trying to isolate for R, you take the opposite of something to the power of 5, which would be its 5th root. And then whatever you do to one side, you do to the other side. So we'll have to take the 5th root on the other side, and the 5th root of 1 over 32 is 1/2. So we've just found out that our common ratio is going to be 1/2. Based off of that, remember, they're saying we want to find out the 13th term in this sequence right here. And so depending on how you want to take a look at something like that, you could say, well, this here was technically the 9th term. So then we would have 10, 11, 12, 13. This was going to be my 13th term right here. And if the common ratio is a half, that means every time you move to the right, you're going to half something. So we could use our TN formula again, but just because we're taking a look at how these patterns emerge, I want to show what's actually happening as we go along. So if you had 125 in this 4th term here, and you times it by a half, you would get 125 over 2. And if you continue to half that, you get 125 over 4, over 8, over 16. And then when you times that by half, you get it over 32. So what's actually happening is your denominator is just doubling every time you move a term over to the right. And so based off of that, you could say, well, this would be 125 over 64, 125 over 128, 125 over 256, and then 125 over 512. And if you can do it that quickly, I would say, don't worry so much about showing your work for something like that, but our 13th term is going to be 125 over 512. Okay, I would say if you're saying like, this is a little bit of a strange question. I would agree with you. I think for example 2 on looking at something with a geometric sequence, it's a little bit of a weird example, and we might want to look at something else in class together just to get us used to this whole idea of how geometric sequences work. Example 3 isn't going to make anything too much easier. This is now something a little more theoretical. We're looking in terms of x's, and they're saying what value of x in the sequence x, 2x plus 2, 3x plus 3 will form a geometric sequence. And so if you want to take a look at something like this, I'm just going to give a side example. Think back to one of our first examples of what we looked at with a geometric sequence. We had something like 2, 6, 18, 54, We can always find the common ratio by taking a term and dividing it by its preceding term. 6 divided by 2 gave us a common ratio of 3. And that would be the exact same common ratio that you would get if you had taken 18 and divided it by 6. So they would be equivalent statements to each other. You could have done that with 54 divided by 18 as well. And so using that idea of being able to find your common ratio by taking a term and dividing it by its preceding term, we can set up a statement here that would be an equivalence ratio. So you could say 2x plus 2 divided by x, the second term divided by the first term, is going to be equal to 3x plus 3 divided by 2x plus 2. And so then both of those would be equivalent to a common ratio. And if you have one fraction and it equals one fraction, you could multiply the diagonals by each other to be able to solve for this. So for instance, you could say here, 2x plus 2 times 2x plus 2 is going to be equal to x times 3x plus 3. So let's FOIL this out and let's see what happens from here. So we get 4x to the 4 plus 4x plus another 4x plus 4 equals 3x squared plus 3x. And let's bring everything onto one side. So let's bring everything onto the left side because we have a quadratic, and we'd be able to, I'm sorry, that should be a squared right there. Because we have a quadratic, and hopefully we'll be able to maybe factor something along the way. So if we do that, we get x squared plus 5x plus 4 is equal to 0, and that is a trinomial that we could factor for x plus 4, x plus 1, which means x could equal -4 or x could equal -1, which means that there should be two answers for something that could work for this to be able to show that that's going to equal a geometric sequence. You could actually take those values for x, you could plug them back in, and that would show that it's making a pattern that is a geometric sequence. Now, in the pattern for x equals -1, it's actually a little bit of a strange pattern where it's going to stay consistent at -1, but I'll show you what I mean by that. So we're saying x could equal -4 or x could equal -1. If x was a -4, let's list what would happen if we substitute in -4 for each of these values. You would get -4, comma, and then if we put in -4 for our second term, you would get -8 plus 2, so you would get -6, and then if you put in -4 there, you get -9, and sure enough, this would equal something that would be a geometric sequence because you're timesing it by 1.5 each time. For our next example here, when you put in a -1 for x, it's a strange pattern. You get -1, 2 times -1 is -2, plus 2 is 0. And then if I put in a -1 here, I get 0 again. And you might say, does this equal something that would be a geometric sequence? It would be a very boring geometric sequence, but technically it has the characteristics of what would satisfy a geometric sequence. Your first term, your a value is -1, your common ratio is 0, and so each time, if you times your terms by 0, you're going to get something pretty boring, and it's just going to say 0, 0, 0, 0 all the way on until however many terms you're looking for. But that does satisfy the characteristics of a geometric sequence, so we're going to say that these two would be our two solutions. Okay, taking a look at that, we'll just go through one more example here. You're going to see a term, and you might remember this back from Math 10 with an arithmetic sequence. They would say something like insert two arithmetic means or something like that to be able to create a sequence. So here we're going to use the term a geometric mean, and it says they're saying insert find the geometric means between 4 and 324. So what it should say is, it should say insert one value in between 4 and 324. It doesn't say that, so it's probably not worded quite as nicely as what we want. But we could say 4 blank 324. Okay, so we're assuming that this means insert one term. Okay, so if we have something like that, and we start at the number 4, and we go from 4 to blank, we're timesing it by a common ratio, and then right here, we're going to times it by another common ratio. And instead of using the T of n formula, I'm just going to try and think of something that could hopefully logically make sense. If we start at the number 4, and you times it by r, and then times it by another r, you'd say 4 times r, or 4r squared, equals 324. So starting at 4, timesing it by r and another r, I end up with an answer of 324. And if we want to isolate for r, we could divide by 4, and r is going to equal plus or minus 9, meaning that when you create a square root, you create a plus or minus situation. So we have positive 9 and negative 9, and what that means is that the blank, what we're looking for, could be positive or negative 36. And that's what would be our solution. Okay, so you have some questions here. Maybe listen for my instructions in class. I think I'm probably going to try and trim this down a little bit. We got a few word problems there. We might not need to go through everything in that full detail for that. So actually right here, this will be a good check to see if you listen to the entire lesson. We'll say this. We're going to omit a couple of these word problems. Let's omit 13, 15, and 17. Don't worry about those three. Okay, so from those word problems from 12 to 18, just make sure you work on the even numbers there, 12, 14, 16, and 18. And then there's some good other questions that you have right here. All right, that's it for today. Thanks.